11713 piping system, presented by Session RA Charles Group A. And here is our group members first.
Okay, Hafiz bin Ahmad Fatih, RU 25113.
Hanis Balkis binti Salim, RA 25112.
And Dayushan RA 25119.
Xin Cicing RA 25120.
Okay, the introduction for our WBP is fluid mechanics plays an important role in civil engineering applications such as water supply and irrigation system. In campus facilities, the piping system are widely used to distribute water for landscape irrigation and daily usage. However, energy losses may occur due to pipe friction, fittings and valves, which reduce overall system efficiency. This project focuses on the analysis of a selected campus piping system consisting of a suction pipe, discharge pipes, elbows, and a foot valve powered by a centrifugal pump. Fluid mechanics theories are applied to analyze flow behavior, calculate flow characteristics, and heat losses, and propose recommendations to improve system performance and efficiency.
Next, we will explain the objective of our project. We have outlined three main goals. First, to analyze the selected piping system using two theories. We will manually to question the continuity and Reynolds number to find the flow characteristics between the compositions. Second, to calculate flow rate and heat loss to determine the flow rates and pressures at various scales in the system and quantity the total energy had available. And the last one is to propose method to reduce energy risks to calculate the energy risks due to pipe friction using series and housing rules equations and minor risks due to valve involved.
Let's talk about distribution system. Is our side view and top view. The fluid transfer system is designed to transport water between two industrial receivers using a multi-diameter piping network. The system physical layout is characterized by specific horizontal span and vertical elevation such as detailed in the technical drawing. Storage tank A, and suction section. From the storage tank A, the fluid enters the system through a 100 mm diameter suction pipe. According to the side view, the pipe maintains a horizontal element for a span of 11,040 mm, where it passes through a centrifugal pump and a gap valve, and the suction line is 400 mm. The water level within tank A is maintained a depth of 300 mm above the pipe center line. Elevation transition and discharge section. The pipe line then undergoes a vertical transition to overcome a static height difference. The side view indicates a final vertical rise of 210 mm before the fluid enters 382,000 in graded in 4,000. So it is a turbulent through the system. Next, we determine the total loss. Here, we start up to 1.54 m. This includes major friction losses and minor losses with components like the thread and ball H equal here H equal cosine 0.204 m and also 0.25. In conclusion, our analysis showed that the 45 mm discharge section is the primary contributor to energy loss. We recognize We recommend use smoother pipe material and reducing the number of the fracture to filter and change system efficiently. So next.
Energy losses in piping system. Energy loss is divided into major losses, friction, and minor losses, fatigue. The total energy loss in a pipe system is the sum of major and minor losses. Major losses are associated with frictional energy loss that's caused by the viscous effect of the fluid and roughness of the pipe wall. Major losses create a pressure drop along the pipe since the pressure must work to overcome the frictional resistance. The Dawes-Fishburne equation is the most widely accepted formula for determining the energy loss in pipe flow based on our fluid mechanics in real application project. First, major losses frictions caused by viscous shear stress between fluid and pipe wall occur continuously along pipe length. 100 mm pipe lower loss due to larger diameter and lower velocity. 45 mm pipe higher loss due to increased velocity and friction, especially along the 450 mm vertical section. Second, minor losses. To localize losses caused by flow disturbances. Significant sources include pipe entrance, vena contractor, and turbulence, valve and pump internal geometry. 390-degree elbow direction change and vortices. Sudden contraction 100 mm to 45 mm, highest minor loss due to rapid acceleration and turbulence.
So this is our recommendations to improve our piping system. First, pipe fittings optimization. We replace straight elbows with long radius elbows to reduce flow resistance and turbulence. Second, material selection used to smoother pipes. Example is PVC to lower friction and reduce major heat loss. Third, system layout improvement. Minimize the fittings and bends to achieve a more direct flow pipe. Fourth is preventive maintenance. Conduct regular maintenance to prevent corrosion and scaling.
Contribution. Based on our analysis using Bernoulli and Fitness equations, we found that the diffuse flux and frequency are the main contributors to energy loss. This is primarily due to the tight fluid velocity in the small pipe and the resistance from minor loss coefficients. To improve the system efficiency, we recommend three changes. First, increase the pipe diameter to reduce velocity. Second, use smoother materials like PVC. Third, simplify the layout to reduce the number of fittings. By implementing this improvement, we can significantly enhance system efficiency and reduce overall energy consumption. That's all.
So here is our reflection. Also, I can
Here's our emphasization. These are the formula that we use in piping system.
that's all for our presented by our work-based project. Thank you.